let's briefly talk about Ohm's law. What is Ohm's law? Ohm's law states that the voltage across a resistor is directly proportional to the current flowing through the resistor. We can say V, our voltage, is equal to Ri. V is voltage, R is the resistance, and then I is the current. The resistance is usually measured in ohms, voltage is measured in volts, I is measured in amperes. R is always greater than or equal to 0. When you look at this simple or basic circuit here, you can see we have circuit element, which is the resistance here, and then which is the resistance, and then we have the voltage with the polarity plus or minus, and then you see the current flowing through the circuit element. The power consumed by a resistor is given as P equal to VI. Okay, and then if we say our V equal to Ri and replace V here with Ri, you will end up with Ri squared. So P can also be equal to Ri squared. If you say from here our I equal to V over R, if you rearrange this and say I equal to V over R, and instead of writing I here, you put V over R here, you will end up with V squared over R. So we can also say that our P equal to V squared over R. So depending on the parameters given to you in an analysis in a question, if you're looking for power, any of these three expressions will surface. So if we have two circuits, if in the first circuit the resistance R1 is greater than the resistance R2, it simply means that the current in the first circuit, current I1 in the first circuit, will be less than current I2 in the second circuit. We do know that I is equal to V over R. So for I1, we have V over R1. For I2, we have V over R2. We've mentioned this before using the mechanical analogy. Now, what we have here is a graph, a voltage current graph. So what are the characteristics of such a graph? What you will see here is that when you plot the graph of voltage on the vertical axis against current on the horizontal axis, and then you find the slope of that graph, what you would have is change in voltage divided by change in current. That is V2 minus V1 divided by I2 minus I1. When you do that, what you end up with is the resistance, because we do know that voltage over current is equal to our resistance. So the slope of a voltage current graph is equal to resistance. And you can see we have V varying linearly with the current in an ideal situation. So what you have here in the circuit is a voltage. You can see the current moving, and then you can see your resistance. You can see our resistance here represented with R, and then you can see that our V equal to Ri, and then R equal to V over I, as we mentioned here in this circuit. In reality, metals have non-linear current voltage characteristics. That simply means that resistance increases with temperature. In reality, that is what happens to metals. Now, let's quickly talk about conductance. Conductance is usually given as the inverse of resistance. It is represented with G, and the unit of conductance is Siemens or mho. The unit of resistance is ohms. And since we're talking about the inverse of resistance here, the unit can then be called mho. And then ohms is also inverted. Okay, so conductance is the inverse of resistance and usually represented with Siemens or mho. All right, if G equal to 1 over R, and we do know from previous explanation that our V is equal to IR, that means our I can be said to be equal to V over R, or can be said to be equal to V multiplied by 1 over R. This simply means that this 1 over R here can be replaced with G. So that means our I, therefore, would be equal to VG. That is how we got this expression here. Okay, and then if you follow the previous explanation too, you know that our P could be equal to IV and could also be equal to, other variations of that particular formula. So if P is equal to IV, that means our P can now be written as I multiplied by V. In this case, our I is VG, so this can be equal to V squared multiplied by G, which is exactly what we have here. Okay, you can also check the second variation, because we know that our G is equal to 1 over R, and we do know also from previous explanation, we know that P could be equal to I squared R. So in this particular case, our R will be equal to 1 over G, because if you rearrange this, R will be equal to 1 over G. So this can then be equal to I squared over G. So these are the variations if you want to use conductance instead of resistance. These are the variations that we can have from the previous explanations. Here is a simple example we can quickly look at. Calculate the value of voltage and current in the following circuits, and secondly, determine the power dissipated in each of the resistors. This is the first circuit. So what you will find out here, in the first circuit is that we have our current. We know that V is equal to IR, that is current multiplied by R, right, by the resistance. Our current here is 1 and our resistance here is 8. So if you multiply this, what you're going to have is going to be 8 volts. So our VA will be equal to 8 volts, which is exactly what we have here. Okay, in the second circuit we have IB. You have to pay attention to the polarities, by the way. That's exactly what this question is trying to point out, the polarities. Okay, so pay attention to that. Here we are using positive current here, all right, because you can see the current is actually flowing from positive to negative. Here the current is flowing from the positive charge to the negative charge, so that is why the current is positive, and then we have our 8 as the resistance. So here it is positive. For B, the B circuit, you will notice that we have current also flowing from positive to negative. Current is flowing from the positive to the negative terminal. So we have IB is going to be equal to, we know that I is supposed to be equal to GV, like we mentioned earlier. So our G is equal to 0.2 Siemens. So you have 0.2 multiplied by our voltage. If you multiply that by voltage, that's multiplied by 50. In this particular case, it will be positive. This will give us 10. That gives us 10 amperes. So that's exactly how we got our IB to be 10 amperes here. All right. In the third circuit, we are looking for VC. What you will find out here that you will see down here that current is not flowing from the positive terminal to the negative terminal. You can see the arrow of the current here pointing downwards. Our normal convention states that current should actually flow from positive to negative. So it should flow this way. But in this particular expression, you see that it is flowing downwards. It's flowing from negative to positive. So in this particular case, our VC will be equal to, our current is 1 ampere. So in this case, it will now be minus 1 ampere, because current is actually flowing from negative to positive. Minus 1 multiplied by 20 ohms that we have, and that will give us minus 20 volts. This is very important. Please pay attention to it. Minus 20 volts. You have to pay attention to the polarities. Also, for the fourth circuit, the D circuit, you will find out that our D is going up here, down this way. So instead of current flowing from positive to negative, also our V is flowing in the opposite direction. So what we are looking for here will be ID. Our ID will be equal to, we know how we call the V over R. We know that's the expression for current. So it will now be equal to minus 50 divided by 25. Again, the minus is because the current is flowing in the opposite direction to our polarity, our sign convention, which is supposed to be from positive to negative, but current is flowing against that. That is why we have the negative here, and our I will therefore be equal to minus 2 amps. Okay. All right, so that's how to find the voltage, the current, the voltage, and the current for the 4 circuits. There's a second part of the question that says, determine the power dissipated in each resistor. Determine the power dissipated in each resistor. How do we do that? The power dissipated in the first resistor here, power, we know that power is equal to IV, and it can also be equal to I squared R. It can also be equal to V squared over R. So in this case, if power is equal to IV, we know that our I is 1, our V calculated is 8, calculated to be 8 volts. So 1 times 8 will definitely just give us 8 watts. You can use any of the expressions of power, you arrived at the same thing. Here they used power is equal to V squared over R is what they used here. So our V is 8, our R is 8. So V squared is 8 squared over R. That still gave us 8 watts. Then the power for the second circuit is going to be equal to, we do know, we had mentioned that for the second circuit, we had mentioned that when we are using conductance, power can be equal to V squared G. Okay, V squared G, as mentioned in the previous explanation. Our V is 50, our G is 0.2. If you multiply those out, that's 50 squared multiplied by 0.2, that will give us 500 watts. In the third circuit, our power would be equal to also V squared over R. Our V was calculated to be 20, so you can have minus 20 squared divided by R, which is 20. That will also give us 20 watts. In the third circuit, we can find it to be I squared R. Our I was calculated to be minus 2, and then you have minus 2 squared multiplied by R, which is 25. That gives us 100 watts. Again, you can use any of the expressions to calculate the power, any of the expressions of power, P equal to IV, P equal to I squared R, or P equal to V squared over R. Any of those three can be used to find our power, and we will still arrive at the same value. All right. Now we're going to quickly talk about independent sources, ideally independent sources. We have a voltage source and then we have a current source. We have an ideal voltage source and we can also have an ideal current source. What is an ideal voltage source? Please pay attention to this. The terminal of an ideal voltage source is constant, regardless of the current flowing in those terminals. This simply means that an ideal voltage source is constant, irrespective of the value of the current flowing in those terminals. The voltage source is independent. That is why they are called independent sources. It doesn't depend on current. It doesn't depend on the voltage elsewhere in the circuit. Its value remains constant irrespective of the current or voltages elsewhere in the circuit. This is very, very important. It doesn't rely on voltages or currents elsewhere in the circuit. And these are the symbols for the ideal voltage source. It could be given as these with a circle somewhere in between, and you can see the positive and negative charge here, and then we have Vs representing the voltage source, and it could also be plus or minus, and then with a V. This is usually like a DC voltage source. This is usually given as a DC voltage source. Okay, then we have the ideal current source. The current of an ideal current source is constant regardless of the voltage across its terminals. This is very important too. This simply means that the values of the current source is constant irrespective of the values of the current or voltages elsewhere in the circuit. It means the value of the current is independent of the voltage and current elsewhere in the circuit. They don't rely on the voltages or current elsewhere in the circuit, and that is why they are called independent current sources. Okay, the symbol is exactly what we have here. You can see the circle here with an arrow pointing down, showing the direction of current, which is flowing down here, and IS represents current source, as you can see here. There's a simple rule we have to pay attention to. Current is assigned such a direction that it always leaves the positive side of the voltage or current. We have to pay attention to this so that we don't get confused when we start analyzing and implementing, the solutions to some calculations. So as I mentioned earlier, this is a voltage source, as you can see here with the circle here. Once you see this bar, a long bar and a short bar connected to cables here, this simply means that it's a DC voltage source. All right, so pay attention to those. Now let's talk about dependent sources. Dependent sources simply means that the sources are dependent. They are relying on other parameters. So we have dependent voltage sources and dependent current sources. Okay, when you are dependent on something, it simply means you are controlled by that thing. Without that thing, you may not be able to function properly. Okay, so the value you take or the position you take will be determined by what is controlling you or by other parameters. So let's quickly look at the voltage, the dependent voltage source. The terminal voltage of a dependent or controlled voltage source depends on the voltage or current defined at some other location in the circuit. And we have two types of this type of dependent voltage source. We have the voltage controlled voltage source. This simply means that the voltage source is controlled by a voltage. And then we also have the current controlled voltage source. This simply means that the voltage source is controlled by current elsewhere in the circuit. Okay, so this is the representation for a dependent voltage source. You can see we have Vs, and then in this time around, it is not a circle, it is like a diamond shape, a kite shape. Okay, and then you can see we have plus, and then we have our negative here between these two terminals. We also have the dependent current source. So the current of a dependent or controlled current source depends or relies on a voltage or a current defined at some other location in the circuit. We also have two types of the dependent current sources or dependent current source. We have the voltage controlled current source. Okay, so that simply means this current source is controlled by a voltage. And then we have the current controlled current source. This means that the current source is controlled by another current in other locations in the circuit. This is also represented with a diamond or a kite shape here, and then you can see IS represent the current source, and you can see the arrow flowing down between these two terminals. Let's talk about series voltage sources. You can see we have a circuit, we have a voltage terminal, and then we have many voltage sources connected in series. So what would be the equivalent of these voltage sources connected in series? The equivalent of the voltage sources connected in series, you can see we have VS1, VS2 as a second voltage right up to VSN, depending on the number of voltage sources that we do have. So the equivalent will be given as Vs, and that would be equal to Vs1 plus Vs2 plus Vs3 up to plus Vsn. So the equivalent voltage source of voltage sources connected in series will be equal to the addition of all the voltage sources. So this is the equivalent circuit here. You can see instead of writing Vs1, Vs2, we now have the equivalent Vs here because we've added all the voltage sources together. So a chain of series voltage sources is equivalent to single voltage source whose source function is the algebraic sum of the series source functions. Let's talk about the series current sources. In this case, we have current sources connected in series. You can see we have IS1, IS2, right up to ISN, depending on the number of current sources that we have. The equivalent circuit will be given as the circuit that you see here. Okay, so for the series current, it simply means they would be the same, they will be equal in this particular case. IS1 will be equal to IS2, which will be equal to IS3, which will be equal to ISN. So they'll be represented by just one single current source because they are expected to be equal. When current sources are connected in series, only one of them is going to be the equivalent current source. So IS will just be equal to IS1 or equal to IS2 or equal to ISN. Okay, the series current source functions have to be all equal in a chain of series current sources, in which case the chain is equivalent to one of them. Otherwise, there is a mathematical inconsistency. This is very important. This last phrase where they said otherwise there is a mathematical inconsistency is important because we are going to look at some questions that would ask us if a circuit is valid or not. Then we have the parallel current sources. In this particular case, you can see that the current sources are connected in parallel. In this case, the equivalent current will be equal to summation of all the current sources. So IS will be equal to IS1 plus IS2 plus ISN. And then this is going to be the equivalent circuit. A set of parallel current sources is equivalent to a single current source whose source function is the sum of the parallel source functions. Again, we have the parallel voltage sources. When we have parallel voltage sources, this simply means that the equivalent voltage source will be equal to one of these. We expect that the voltage sources will be the same. So VS1 is going to be equal to VS2, it's going to be equal to VSN, and that will be equal to VS, which is going to be the equivalent voltage source. All right, please pay attention to these. A set of voltage sources in parallel must have equal source functions, in which case any one of them is equivalent to the entire set. Otherwise, there is a mathematical inconsistency. Again, you need to pay attention to this last phrase. Otherwise, there is a mathematical inconsistency, because we'll be dealing with questions that would be related to this directly. Here's a simple example here. For the circuit shown, what value of VG is required in order for the interconnection to be valid? For this value of VG, find the power associated with the 8 ampere source. Again, what you will find here is that there are 3 sources. You can see we have the first source here. This is a dependent source, like we mentioned earlier. This is a dependent source. And what kind of dependent source is this? You can see we have IB over 4. This is a current controlled dependent source. Then this is another source. This is a voltage source. And then this is another source, which is a current source. So the first question says, what value of VG is required in order for the interconnection to be valid? We had said that for the interconnection to be valid, when we have voltages, interconnected in a circuit. So for the interconnection to be valid, since these are connected in parallel, this source is connected in parallel to this source, it simply means this voltage has to be equal to the voltage here. VG on this source has to be equal to the voltage on this particular source. All right, so how do we find the voltage on the dependent source? We know that our IB would be equal to -8, because 8 amperes is actually pointing downwards. So 8 amperes is pointing downwards, as you can see with this arrow. Any current that is pointing against this arrow pointing downward would take a negative value. So as you can see, IB is actually going up, as you can see. So IB will be -8 amps. If IB is -8 amps, it simply means if you put -8 amps here, because there is IB here, if you put -8 amps here, that would be -8 over 4. So you would have -2 volts on this dependent source. That means this voltage here is -2 volts. Since this voltage is -2 volt, and we said VG has to be equal to the voltage here because they are connected in series. Again, from the previous explanation we just gave, you would get that concept. So VG would be equal to -2 volt. In the question, they said what value of VG is required in order for the interconnection to be valid. For this interconnection to be valid, VG has to be equal to -2 volt. Okay. Again, the next question says for this value of VG, find the power associated with the 8 ampere source. What is the power associated with the 8 ampere source? So from what you can see here, you see that we found our IB to be equal to -8. We found our VG to be equal to -2 volt. Then the power associated with the 8 ampere source will be equal to current times volt. The current is 8 amperes, right? And then the volt is going to be equal to -2. Okay, the voltage that is seen by this current is -2 volt because VG is -2. So we have -2 multiplied by 8, and that would give us -16 watts. In this particular case, it simply means that power is being delivered or generated. It is not consumed. If it is consumed, we would have a positive power. But because we have a negative power, it means the circuit element is actually delivering or generating power. Okay, and the amount of power being delivered or generated is 16 watts. That is what this negative value represents. So this is an example. You might need to go over this again so you can get a better understanding. Here is another example we can easily look at. If the interconnection in the below figure is valid, find the total power developed by the voltage sources. If the interconnection is not valid, explain why. You will see that from this particular loop, 5 amperes and 4 amperes are actually connected in series because the current that flows through here is expected to continue to flow and continue that way. So this current that flows this way and goes this way, it is 5 amperes from here and it is 4 amperes here. It means that they are connected in series and they are not the same. So we can easily say that this particular circuit is not valid. This configuration or this interconnection in this circuit is not valid. Okay, we will quickly talk about short circuit. A short circuit is a perfect conductor or a conductor with zero resistance. Two nodes can be short-circuited by connecting them with a wire. A short circuit can sustain current without any voltage drop. In reality, there always is a maximum current limit after which damage occurs to the material. So what we're saying here is that for a short circuit, the voltage is usually zero for a short circuit. So we usually have what we refer to as the I short circuit or short circuit current. Okay, that is the current we obtain when the voltage is zero. Okay, and that simply means when voltage is zero, that means we have zero resistance, and then that's the maximum current is allowed to flow because there is no resistance at all. And in that particular case, the voltage is zero. You can the two nodes can be short-circuited when you just connect them with a wire. Okay, so please pay attention to that. Then we have what we refer to as an open circuit. An open circuit is perfect insulator. It works as an insulator, while a short circuit works as a conductor, conducting. Okay, it works as a perfect conductor. It conducts every current that is flowing. No resistance at all. Nothing is stopping the flow of current. For the open circuit, it works as a perfect insulator. This simply means that it works in such a way that it doesn't allow current to flow. So the current when we have an open circuit is usually assumed to be equal to zero. In this case, we have what we refer to as the open circuit voltage, which is the maximum voltage possible across a particular circuit or across a particular circuit element. So an open circuit is a perfect insulator or resistor with zero conductance. It doesn't conduct any current at all. An open circuit can sustain any voltage without any flow of current. Again, there is always a maximum practical limit after which breakdown occurs. So we usually have open circuit voltage VOC and short circuit current ISC. Remember, when we have a short circuit current, the voltage is zero. When we have an open circuit voltage, the current is zero. Open circuit voltage simply means that current is not allowed to pass through the terminals. So we have maximum voltage, current is zero. For the I short circuit, we have the maximum current possible. A short circuit works as a perfect conductor. We have the maximum current. It conducts as much current as possible. It allows as much current as possible to pass through the terminals. So in this particular case, we have I short circuit but zero voltage. Please pay attention to this. It is important. This is where we are going to stop for the lesson. I will see you in the next lesson. If you like this video, if you enjoyed this video, please give it a thumbs up and subscribe to this channel by clicking on the subscribe button. Also click on the notification button so that you get notifications when new materials are uploaded on this channel. I would also like to know what you think about this video, so feel free to drop a comment in the comment section. Let me and others watching this video know what you think about this video and lesson. Alright, do have a wonderful time and I'll see you in the next lesson.